Hey you guys, welcome back to another video. Today we're going to be combining lesson 9 and 10. We're going to be covering the vertical asymptotes and wholes of rational functions. Recall that a rational function is the quotient of two polynomials. A rational function could be y equals f of x divided by g of x, where f of x and g of x are both polynomials. Since we are dividing by a polynomial, rational functions have restrictions on their domain. We know that we cannot divide by 0, so we must consider any x values where g of x equals 0 and restrict them from the domain. These x values will be the location of either a vertical asymptote or a hole in the graph. Vertical asymptotes and holes both occur when the denominator of a rational function equals 0. So how can we distinguish between the two when working with a rational equation? A hole occurs when the factor in the denominator cancels out with factors in the numerator, and a vertical asymptote occurs when a factor in the denominator cannot cancel out with factors in the numerator. Okay, let's focus on holes first. We have two examples here, f of x and g of x. On f of x, we have x minus 1 times x plus 2 divided by x minus 1. Notice that the factor x minus 1 appears in both the numerator and the denominator, so you would cancel them out. Anytime you cancel something out, that's going to create a hole. What you do to figure out the coordinate of the hole is set the factor that appeared in both the numerator and the denominator, in this case x minus 1, and we're going to set it equal to 0. If you add 1, here you get that the hole is at x equals 1. Now, in lesson 8, we talked about how after you cancel out any common factors, whatever is in the numerator will be your 0. So this here would be the 0. And to find that, you set that factor equal to 0, and we have a 0 at x equals negative 2. Okay? Now, there's another equation, another example, g of x equals x minus 1 cubed divided by 2 times x minus 1 squared. Now, if you wanted to write this out, x minus 1 cubed means that you're multiplying x minus 1 by itself 3 times. And in the denominator, we're multiplying it by itself 2 times. Now, if you write it out this way, you'll see that this x minus 1 cancels out the 1 down here, and this one cancels out 1 there. So what we have left over is an x minus 1 in the numerator and a 2 in the denominator. Okay, so since we canceled out 2 of the x minus 1s, that will also create a hole. We would set that factor equal to 0, and we would get x equals positive 1. Okay, now if we continue on the same process as earlier, whatever we have left in the numerator would be your 0. So since we had this factor left in the numerator, I would say that we have a 0, and we would set that factor equal to 0, and we would get x equals positive 1. Now we run into an issue because we said we had a hole at 0 and a hole at x equals 1 and a 0 at x equals 1. Now it is impossible to have a hole have a 0 in the middle of it. So what actually happens here is that if they're in the same location, that 0 no longer exists. Okay, so I'll make a note of that over here. So a 0 cannot have the same x value of a hole. Okay, because if you think about it, a 0 is a defined point, right? So let's say I have a graph, and then at 0, we're saying, at x equals 1, we're saying we have a 0, but then also at 0, we have a hole. You can't have a 0 inside of a hole, okay? The hole means that there is nothing defined at that point, so therefore the 0 inside is not true anymore, okay? So this one just has a hole at x equals 1. Now, if you're looking at this graphically, you can identify what the holes are because it'll be a little open circle on the graph like this one. This one is also at x equals 1. And all holes have a y coordinate. So this one, the hole is at 1, 3. So again, this is the hole. The x coordinate is 1 and the y coordinate is 3. Okay, now I'm going to introduce limit statements. we did limit statements for n behavior, which is all the way to the left and all the way to the right to positive and negative infinity. This is going to be a little bit different. You can see that underneath here we have as x approaches 1, x approaches 1. Now that is coming straight from the x coordinate of the whole. So what you write down here is the x coordinate of the whole. Now you might notice this little minus and plus. Notice that it is not in the front, okay? So this is not saying x is approaching -1. It's saying 1 from the left, okay? That little minus and the little plus is going to indicate what direction you're going to be looking from. So the minus means left and the plus means right. So when you read this, you'll say the limit as x approaches 1 from the left, f of x equals 3. Or the limit as x approaches 1 from the right, f of x equals 3. Okay, now notice that both of them have 3 as the answer. The reason for that is that the answer for both the left and the right limit will be the y coordinate of the whole. Okay, so if you look at the graph again, now when you're looking from as x approaches 1 from the left and 1 from the right, you want to look really, really close. So first identify where 1 is at. Okay, so x equals 1 is right here on the x-axis. There, that's better. Now you don't want to look too far, okay? If I say the left of the whole, I mean like really close here. Yes, all of this is also to the left, but that is too far. Okay, so when I say look to the left of 1, I want you to look immediately before 1. Okay, so for example, we can look something like this close. You don't want to look all the way over here. This is too far to the left and this is too far to the right. You want to focus and zoom in at only what is happening right before you get to +1 from the left side and what is happening after. So this is the left of the whole and this would be the right of the whole. Okay, so as we come in from the left of the whole, you can see that my y values are approaching 3. If I come in from the right going towards the whole, again, my y values are approaching 3. So from both directions, I'm going to be coming in towards the same exact y value, which is at y equals 3. Okay, so that's how you do the limit for the wholes. Now let's go on to vertical asymptote. So here we have two equations. Notice that for f of x, none of the factors are the same, so nothing cancels out. Okay, what we have left in the numerator are the zeros. So remember that for zeros, you set the factors equal to 0. So everything at the top would be a 0. So we have zeros at x equals 3 and x equals -2. In the denominator would be your vertical asymptote. So you would set that factor equal to 0 and you get a vertical asymptote at x equals 1. Okay, so that's if nothing cancels out. Now for g of x, notice that we have 2x minus 1 squared. We have it squared at the bottom, meaning that there's 2 of them. I can rewrite this as x minus 1 times x plus 2 divided by x minus 1 times x minus 1, because when you square something, that just means you're multiplying it by itself. Okay, so what happens is that these two factors cancel out. That creates a whole. Okay, so we have a whole. You set that factor equal to 0. You have a whole at x equals 1. What you have left in the numerator is your 0. Set the factor equal to 0. We have a 0 at x equals -2. What you have left in the denominator is your vertical asymptote. You set that factor equal to 0. We have a VA at x equals 1. Now notice that we have a vertical asymptote and a whole both at x equals 1. When that happens, it is not possible. Okay, think of a vertical asymptote being like the strongest of all of these. It is going to completely overpower this whole, making the whole non-existent. So the same way that on this side, we could not have a 0 and a whole be in the same location, the same thing applies here. Okay, so I'm going to make a note of that. So A whole cannot be at the same location of a vertical asymptote. Okay, I'm going to give you another trick that's going to help you because a lot of the times you're going to use the same factors like on this side and on this side, but they're going to involve exponents. So it's going to be an easier way for you to figure out, well, is it a whole or is it a vertical asymptote? Okay, so notice that on this side, underneath the wholes, I have on g of x, the factor was cubed in the top and squared at the bottom, meaning that there was always going to be one more at the top. If that happens, that factor is going to be a whole. Okay, so if a common factor has a higher degree, remember that degree means exponent. So if it has a higher degree in the numerator, then you have a whole. Okay, but if the opposite is true, okay, so here x minus 1 had a power of 1 in the numerator and a power of 2 in the denominator. If the opposite is true, if it's bigger at the bottom, then you have a vertical asymptote. Okay, so if a common factor has a higher degree in the denominator, then you have a vertical asymptote and you do not have a whole. Okay, all right, so let's look at this graph. Here we have a vertical asymptote at x equals 1. You can see this dashed line here. They do not always have to give you a dashed line, so please do not rely on the dash to identify the vertical asymptote. Okay, and then for the limit statement, it's similar to the whole. You have the x approaches 1 for both the left and the right side, and that will also be the x value of the whole. Of the vertical asymptote. And then we still have the minus and the plus to let you know if it's the left or the right side. Now, the first part is the same as the whole, but the answers are different because if you remember for the whole, the answer was a number and it was the same number on both sides. For vertical asymptotes, it'll be a variation of either positive or negative infinity. So what you do is similar to what we did in the whole, which is we're going to isolate x values. We're going to locate x values that are really close to the vertical asymptote. So again, I want to be immediately to the left, like right here, and then just immediately to the right, like this. Okay, so again, this is the left of the vertical asymptote, and this is the right of the vertical asymptote. So you don't want to focus on any of this over here or any of this over here. You want to zoom in exactly to where x equals 1. Okay, so I'm going to zoom in first to the left side. I'm going to analyze here. I don't have anything. Oh, wait, and then I see the graph. Okay, so here, immediately to the left of the graph, my y values are going down. Okay, so what I'm going to do is I'm going to draw an arrow going down. I'm going to circle that and I'm going to annotate that from the left side, I am going down to negative infinity. Okay, now let's repeat that with the right side. On the right side, as soon as I look at the right side, I see the solid black line. Those are my y values. If I were to trace that on immediately to the right side of this green vertical asymptote, my y values are going up to positive infinity on the right side. Okay, so on the left, here's the VA. On the left of the VA, I was going down. On the right of the VA, I'm going up. So that's why the limit on the left was negative infinity because I went down on the left. And for the right, it was positive infinity because we went up on the right. Okay, now let's do some more limit statements just for practice. On this graph, we also have a vertical asymptote. I have a vertical asymptote at x equals -1. I'm going to annotate that, VA at x equals -1. Now, I can write limit statements for this one as well. I can say the limit as x approaches -1 from the left, f of x equals, and the limit as x approaches -1 from the right, f of x equals. Okay, so if I look just to the left of the vertical asymptote, I can see that these y values are going down. Okay, so that means that my left limit will be -infinity. And if I look just to the right of the vertical asymptote, I see that my y values are going up to +infinity. So on the right side is going up to +infinity. Okay? Now, those are not the only limit statements we have done. We've also done end behavior. In lesson 7, we did limit statements that look like this. The limit as x approaches -infinity, f of x equals something, and the limit as x approaches +infinity, f of x equals something else. Now, -infinity will always mean all the way to the left, and this one means all the way to the right. Okay, so this one, instead of focusing at a particular x value, like when we did -1 and +1, for the left, you're going to zoom in all the way to the left. You don't want to see anything else that is not on the left. Okay, now if I were to trace these y values all the way to the left, I see that these y values do not go up or down, but I do notice that they're forever on this horizontal asymptote, which is at y equals 2. So I know that these y values cannot go up, and I know that they cannot go down. These y values are going to stay forever getting closer and closer and closer to 2, although they never equal 2 because it's not going to cross the horizontal asymptote, but it is going to stay getting really, really close to +2. Therefore, the limit statement all the way to the left would be equal to +2. Okay, now let's look at the right side. I'm going to zoom in all the way to the right of this graph. Same thing happens. And if I trace these y values, they're not going up. This arrow does not indicate that it's going up or down. You can see that the y values stay constant and they're hovering over the horizontal asymptote, which is at y equals 2. So for the left and the right side, the end behavior goes to +2. Okay, so those are 3 different limit statements. So just to clarify, these 2 up here are for the hole. These 2 here are for the vertical asymptote. And these 2 here are for the end behavior, which we calculated using the horizontal asymptote. Okay? Now we can do the same thing for this side because this one also has a horizontal asymptote at y equals 1. So if I wanted to write the limit statement, I would say the limit as x approaches -infinity, f of x equals, and the limit as x approaches +infinity, f of x equals something. Okay, so again, if I focus all the way to the left, I don't want to see anything in the middle or the right. You see how these y values, they don't go up or down. They stay there, getting closer and closer to the horizontal asymptote, which is at +1. And the same thing on the right side, the y values don't go up and they don't go down. They stay constant, getting closer and closer to y equals 1. So for these limits, the answer would be 1. Okay, so again, this one was for the vertical asymptote, and this was for end behavior. End behavior is what happens all the way to the left and to the right, and to figure it out, we used the horizontal asymptote. Now, this graph didn't have a hole, so I can't show you the limit for the hole, but we'll do some more examples later on. Okay, let's go to the next page. Example 1 says for each of the function, determine the x values of any holes or vertical asymptotes. Okay, starting with f of x, I see that there is a common factor of x plus 3 on both the numerator and the denominator. Anything that cancels out is your whole, and you set that factor equal to 0. So we have a whole at x equals -3. Okay, now whatever is left over in the denominator would be the value of your vertical asymptote. Set the factor equal to 0, and we get a vertical asymptote at x equals +5. Now it's very important that you do write x equals. If you just say the VA is at 5, the whole is at -3, that will be considered wrong. It needs to have the x value, okay? X equals and then the number. They didn't ask for the zeros, but if you really wanted to, the zeros are anything that is left in the numerator. So the zeros here, we would do x minus 2 equals 0, and we would have a 0 at x equals 2. Okay, let's move on to B. So I have kind of the same factors. I have x plus 1 and x plus 1 squared, and then x minus 2 squared. Now, the exponent of both of these is 1 because they didn't have an exponent, okay? Now, if I analyze the exponents here, and then if I analyze these here, remember, if the exponent is bigger in the numerator, then it is a whole. So this one that has a bigger exponent of 2 in the numerator will end up being a whole. So I'm going to set that factor equal to 0 and say that there's a whole at x equals 2. Now this factor, there's a power of 1 at the top and a power of 2 at the bottom. Since the exponent is bigger in the denominator, that's going to make that factor be a vertical asymptote, which I can set that factor equal to 0, and I would get x equals -1. Okay, so again, if the exponent or if the degree is bigger on the bottom, then it's a vertical asymptote. Okay, if the degree is bigger on top, then you have a whole. Okay, let's move on to the next one. Now, I don't see anything that cancels out, but I also don't see any factors. That's an indicator to me that I need to factor this. Now, I can't factor 1, but in the denominator, I see that I have a greatest common factor of x. If I take an x out of there, I would be left over with x times x squared plus 4. Okay, again, nothing cancels out, so that means that there are no wholes. You do not always need to have a whole. Okay, now for the vertical asymptote, you set the entire denominator equal to 0. Let me put it over here instead. We're going to do x times x squared plus 4 equals 0. Now, when you have two factors like this, you do have to separate them and set each of these factors separately equal to 0. Now, x equals 0, you can't do anything else to it, so I know that for sure there is a vertical asymptote at x equals 0. Okay, let's solve the other one. I'm going to subtract 4. That's going to give me x squared is equal to -4. I need to square root this. These two cancel out. Every single time you take the square root of a number, you need to remember to add the plus or minus symbol. The square root of 4 is 2. And I do have a negative under the square root, which means that's going to give me an imaginary I. Okay, now this is not going to work. Okay, so I'm going to cancel this out. Your vertical asymptotes cannot be imaginary. So this one has no wholes and only one vertical asymptote at x equals 0. Okay, let's go to the next one. Write a left and right limit statement as x approaches 2 for each of the following functions. Now you're going to want to pay special attention to this part here, as x approaches 2. That's going to tell you exactly what number you need to be looking at. Okay, let's start with A. I don't see any wholes. Nothing seems to be canceling out here. If I were to solve for the zeros, I would get a 0 at x equals +1 and x equals -3. And if I look at the bottom, I have a vertical asymptote at x equals 2. Okay, now the question said as x approaches 2. These zeros do not equal 2, so I'm not going to focus on that, but I do have a vertical asymptote at x equals 2, so I want to use that one because it answers the question. They wanted me to focus on x approaching 2. Now, the vertical asymptote, remember that on the left or the right side, you're either going to be facing up or down. To figure out whether you go up to infinity or down to negative infinity, you need to make a number line like we did on lesson 8. The only difference is that on lesson 8, we did the entire graph, okay? We figured out if it was above or below the x-axis starting from negative infinity all the way to positive infinity. We don't need to do that for this problem because I only care about what's happening immediately to the left of the vertical asymptote and immediately to the right. So the only number I'm going to place on this number line is 2. Okay, now I want to think of a number that comes right before 2, but not too far away. Because remember, you don't want to be far. So think of a decimal that's right before 2. I can think of 1.9. And right after 2 would be 2.1. Okay, now what I'm going to do is plug these into all of these factors here. 1.9 minus 1 would be positive. 1.9 plus 3 is positive, and 1.9 minus 2 is negative. This interval would end up being negative. If I do 2.1 minus 1, that's positive. 2.1 plus 3 is positive, and 2.1 minus 2 is also positive. So this side is positive. Okay, so this is going to help you do your limit statements because this is the left side. The left side goes down to negative infinity, and the right side is going up to positive infinity. Okay, so when you write your answer, you're going to say the limit as x approaches 2 from the left, f of x equals negative infinity. For the right side, the limit as x approaches 2 from the right, f of x equals positive infinity. Okay? Now, let's go on to the next problem. Now, in this problem, I do see a hole because these two factors cancel out. So I know that I have a hole at x equals 2. I know that I have a 0 at x equals negative 4 and a vertical asymptote at x equals 3. Again, the question was as x approaches 2. The only one that gives me 2 is the hole. I'm not going to use the 0 or the vertical asymptote because they don't answer the question. If the question had said as x approaches 3, then I would be choosing this one and not that one or this one because they don't have the same number. But for this one, we're going to use 2, which is the hole. Now remember, for the hole, the limit is a number, and that number is the y-coordinate of the hole. So how can we figure out what the y-coordinate is? All you have to do is plug the hole back in. So we have g of 2, and now you're not going to plug it back into the factors that you canceled out. Okay, so now we have 2 plus 4 divided by 2 minus 3. 2 plus 4 is 6. 2 minus 3 is negative 1. When you divide that, you get negative 6. Okay, so now we have the limit as x approaches 2 from the left, g of x equals negative 6. And the limit as x approaches 2 from the right, g of x equals negative 6. Okay, so just as a recap, we got the hole at x equals 2. I plugged 2 back into what was left over. So g of x was equal to x plus 4 divided by x minus 3. And I plugged in the x coordinate of the hole. Okay, we plugged in the x coordinate of the hole and we got the y coordinate. This is the y coordinate of the hole. I abbreviated coordinate. But yeah, so it's pretty easy when you have a hole. All you have to do is plug it back in to the factors you have not canceled out. Okay, let's do h of x. All right, I see that I have x minus 2 in both the numerator and the denominator, but the one in the numerator has a power of 1. So if I analyze the exponents, I see that the exponent, the degree, is bigger in the denominator, so I know that this is going to be a vertical asymptote at x equals 2. I also have another vertical asymptote at x equals 1, and I have a 0 at x equals 4. Okay? Now, remember the question. The question said, find the limit as x approaches 2. I'm not going to use 4 and I'm not going to use 1. I'm going to focus on this vertical asymptote at x equals 2. Okay, you have to answer the question. If the question said as x approaches 1, then I would have used this vertical asymptote and not that one, but that's not what the question is asking. They want us to find as x approaches 2. So anytime you have a vertical asymptote, you need to create a number line, put the x value of the vertical asymptote that they want. You're not going to put both. I know that there are two vertical asymptotes, but you're only interested in the one at 2, okay? Pick a number really close, such as 1.9 and 2.1. Now, earlier in the previous example, you might have been asking, well, why do we have to be so close? Why couldn't I pick 1? You know, like here when I said pick a number before 2. Maybe you wanted to test 1 and 3. Yes, those numbers are just before 1 and just after 2. Just before 2 and right after 2. Yes, they are. I could have picked 1 and 3, but they are too far away. You need to make sure that you're using really close decimals, because what could happen? I could have another vertical asymptote at x equals 1. And if you had been comfortable using 1 and 3, now you run into an issue and it's not going to work because you're too far away from 2, and now you actually have another vertical asymptote. Or maybe you have a hole, and if there's something else at the place you're trying to test, it's not going to work. So to avoid making that mistake, don't use whole numbers, just use a really, really small number close to wherever the vertical asymptote is that you're testing, okay? Now let's plug it into the factors. 1.9 minus 4 is negative. 1.9 minus 2 is negative. Any factor that is squared is always positive. 1.9 minus 1 is positive, making this interval positive. Okay? 2.1 minus 4 is negative. 2.1 minus 2 is positive. Any factor that is squared is positive, and 2.1 minus 1 is positive, making this interval negative. Okay, so remember, this is your left side and this is your right side. So your left side is going up while your right side is going down. So for the limit statement, we'll say the limit as x approaches 2 from the left, h of x equals positive infinity. And the limit as x approaches 2 from the right, h of x equals negative infinity. Okay? Now, I just want to zoom out and show you the question said as x approaches 2. We used x approaches 2 for every single limit statement, and then all we did for the left was add the little minus at the top, and for the right, a little plus at the top. So when they ask you to find x approaches 2, all of your answers should already start with the limit as x approaches 2 from the left and the right, okay? Let's move on. We're going to be writing equations of rational functions with the following limit properties. Okay, so I'm looking at this and I see that these have x approaches 3, and I also see x approaches 1, x approaches 1. I know for sure that this is not going to be end behavior. It's not going to be a horizontal asymptote. Why? Because we talked that horizontal asymptotes, it's as x approaches negative infinity and x approaches positive infinity. Okay, remember we talked about that here. For end behavior, when we use the horizontal asymptote, underneath the limit statement, we always have x approaches negative or positive infinity. Only for the holes and the vertical asymptotes did we have some kind of numerical number underneath. Okay, so I know for sure that two limit statements they gave me in that example is either a hole or a vertical asymptote. I also know that a hole always has a numerical answer, while vertical asymptotes will have a variation of positive or negative infinity. Okay, so if I look at the top two, I see x approaches 3 from the left and x approaches 3 from the right, and they both equal 5. That lets me know that these two are referring to a whole, okay? And the bottom one, as x approaches 1 from the left and the right, is either positive or negative infinity. So I know that that has to be a vertical asymptote, okay? Now, in factored form, we don't use the y values, we only use the x values. So the whole underneath the limit statement says x approaches 3. That lets me know that the whole is exactly at x equals 3. If I were to write that in factored form, it would be x minus 3. Okay, now for it to be a whole, that factor needs to appear in both the numerator and the denominator. If it's not on both the top and the bottom, it's not going to cancel out to create a whole. It has to be in both. Okay, now for the vertical asymptote, the limit statement says as x approaches 1. That lets me know the vertical asymptote is at x equals 1, and the factor would be x minus 1. And vertical asymptotes come from the bottom. Okay, now we haven't talked too much about how horizontal asymptotes can affect the graph, but they go on the outside of the function. So when we write f of x, now we would have on the top and the bottom, we would have x minus 3. And on the bottom only, I would have x minus 1, okay? But what we haven't talked about is that there could be a number. I'm going to use the letter k to represent a number that we can multiply by that would represent what the horizontal asymptote would be, okay? So, not just a horizontal asymptote, but it could be if I'm shifting the graph up or down, or if it's just a multiplier, if I'm vertically stretching or dilating. We'll talk about transformations of functions in lesson 12, but there could be something that's affecting the graph that's making it move up or down or getting stretched or compressed or something like that. Okay, now to figure out what the k value could be, I am going to use the whole. So if I were to cancel out x minus 3, I would be left with k divided by x minus 1. If I use the whole is at x equals 3. Okay, so I would get k divided by 3 minus 1. I also know that when f of 3 has to equal 5. How do I know that? Because they gave me the y coordinate of the whole. Okay, this y coordinate is f of 3. F of 3 equals 5. When x is 3, y is 5. F of 3 equals 5. It's the same thing, just a different notation. Okay, so I can say k divided by 2 is equal to 5. And now the only thing that k could be is 10. Okay, so if I really wanted to make this equation really correct, I would say f of x is equal to 10 divided by x minus 3, times x minus 3, divided by x minus 3 times x minus 1. And that would be the correct equation there. Okay, let's try another one. All right, so I see underneath the limit statement, I have x approaches negative 2 from the left and x approaches negative 2 from the right. And I see that these are equal to a numerical number, so I know that these two are going to be referencing the whole. Underneath that, I have x approaches negative 1 from the left, x approaches negative 1 from the right, and they're both going up to positive infinity, so I know that this is going to have to be the vertical asymptote. Okay, so if I look at the whole, it says that x approaches negative 2 means that the whole is exactly at x equals negative 2. The factor would be x plus 2. And you would have to write this on both the top and the bottom of the fraction so that they cancel out. For the vertical asymptote, it would be at x equals negative 1, and the factor would be x plus 1, and it has to appear only on the bottom. Okay? Now, there's one thing that we haven't talked about, and that is the what possibilities the vertical asymptotes could be. So we have talked about vertical asymptotes going up on the left, down on the right, or down on the left, up on the right. But what we haven't seen is when they both go up to positive infinity, they could also both go down to negative infinity. And what determines that is the multiplicity of the factor. Let me graph one so I can show you. And I'm going to just do a basic one. Let's say I have 5 divided by, let's say, x plus 2. Okay? And let's say I give this an exponent of 1. Okay? So you see it goes up on the right and down on the left of the vertical asymptote. Let me put the vertical asymptote on there so you can see that. Actually, I don't think I can do it. That's fine. Okay, so that would be for the power of 1. Now let's try something like the power of 3. It doesn't change it that much. It's still going up on the right of the vertical asymptote and down on the left of the vertical asymptote. But what do you think would happen if I were to change that exponent to squared? Now they are both going up in the same direction. They both go up to positive infinity, both on the left and the right of the vertical asymptote. Okay, let's try another exponent. Let's say I put to the power of 4. Okay, they're still both going up to positive infinity. So what that means is if the factor that your vertical asymptote is coming from has an odd exponent, then the vertical asymptote will have opposite behaviors on either side of the vertical asymptote. But if the factor has an even exponent, then both sides will be going in the same direction. Okay, now what would happen if I were to make this a negative fraction and I kept the power of 4? Okay, if I were to add a negative leading coefficient, now both of them are going down. Okay, so back to the notes. Because both of these are going up to positive infinity, I know that this vertical asymptote needs to have an even degree. If it has an odd degree, then they would be going in opposite directions. Okay, but because they have the same direction, I need to make this an even degree. So this factor of x plus 1, I'm going to add a power of 2 on it. It could be anything you want. You could do the power of 4, the power of 6. I'm just going to do squared to keep it easy. Okay, now if I were to put this together, we would have f of x equals, and then in the numerator, we need to have x plus 2. We also need x plus 2 in the denominator, and then an x plus 1 squared. Okay, now don't forget that there is something getting multiplied outside, and I'm going to use k to as a placeholder, and we'll come back and solve for k. So if I cancel out the whole, I would just have k divided by x plus 1 squared. I'm going to use the whole again, which was at x equals negative 2, and then I'll plug it in, get negative 2 plus 1 squared. And the whole was at positive 4. Okay, so if I were to simplify that, I would have k over negative 2 plus 1 is negative 1, and negative 1 squared is positive 1. And that has to equal 4. So the only thing that k could be is positive 4. Okay, which means that my final function would be f of x equals 4 divided by, times x plus 2 divided by x plus 2 times x plus 1 squared. Okay, and that is the answer there. All right, 2 more examples. We're going to be sketching a picture of a rational function with the following properties. Okay, f of x has a whole at x equals 1, and as x approaches 4 from the left, f of x increases without bound, and as x approaches 4 from the right, f of x decreases without bound. Okay, if I were to write this in limit notation, I would say the limit as x approaches 4 from the left, f of x increases without bound means it goes up to positive infinity. The limit as x approaches 4 from the right, f of x decreases without bound, meaning negative infinity. Okay, and we don't really know how to write the limit for the whole, because what do we need for the answer? That's right, you need the y coordinate. So we're unable to finish that off, but let's start with at least the vertical asymptote. Again, if you have a number underneath the limit statement that equals positive or negative infinity, that is indicative that you have a vertical asymptote. And this vertical asymptote is at x equals positive 4. How did I know that? Because they said as x approaches 4, and it was a positive 4 from the left and the right. So I'm going to start by plotting my vertical asymptote. Let's say this is positive 4. Okay. Now it said on the left, I'm going up. So on the left of this vertical asymptote, I'm going to draw an arrow going up. On the right, it said I'm going down. Okay. So remember, this is the left of the VA and this is the right. So on the left, it said I'm going up. On the right, I am going down. Okay. Now, they didn't tell me exactly where the horizontal asymptote is, so I don't know if this graph is going to be like this, or it's going to be more like that, or like this. If they had told me where the horizontal asymptote was, I could do a better picture. For this case, I'm just going to make my horizontal asymptote be at 0 to make it easier. And I'll just follow this like this, because remember, the graph never crosses the horizontal asymptote, so it'll just stay like this. And then same thing here, it's not going to cross the horizontal asymptote. I'm just making one up at 0 because it didn't provide that information on the question. Okay, now the only information we have not used is that there is a hole at x equals 1. So now what I'm going to do is I'm going to just figure out where I think x equals 1 would be, and I think it would be like right here, and I'm just going to erase whatever I had drawn there, and I'm going to put a little open circle to indicate that that's where the hole is at x equals 1. Okay, because they didn't tell us what the y value was, so I can't make it more accurate than that, but that would be a a potential sketch. Again, it's not perfect. It could have been more like this. They didn't tell us where the horizontal asymptote was, so it's just a rough sketch. Okay, so here we have another example. As x approaches negative 1 from the left, the limit as x approaches negative 1 from the left, g of x decreases without bound, meaning it goes down to negative infinity. And this one, the limit as x approaches negative 1 from the right, g of x decreases without bound, also going down to negative infinity. For the holes, I don't have the y coordinate, so I can't be that specific with them, but let's draw the vertical asymptote, because I know that there has to be a vertical asymptote at x equals negative 1. Somewhere right here. And it said that on the left I'm going down, but it also said that on the right I'm going down. So on both sides of this vertical asymptote, I am going down. Okay, now I don't know where the horizontal asymptote is. It could be here, and let's say I'm going up like that, or it could be at 0 and I'm just going like this. I don't really know. It could be a slant asymptote and I go like this. It's hard to tell depending on we're missing some key information here, but again, this is just a sketch, so it doesn't have to be perfect. So let's just say I draw it out like this, and then I would add my holes at negative 2. So let's say I have a hole right here at negative 2. So right there, x equals negative 2 for the hole. And then at positive 3, let's say that's somewhere over here. These are really big holes, but it's okay. It's just a sketch. And so that's what the graph could look like. Again, there's a bunch of different possibilities, and we would be able to do a better job if we had some more information. But this is okay. It answers the question, which is what they wanted. Okay. If you guys have any further questions, please leave me a comment down below, and I'll see you guys in the next video. Bye.